All right, 7.6. The first 10, we're supposed to try to identify just what we would try to do these. Now, the first one is not one that looks like much of anything we've done. The only thing we might possibly do is try to complete the square on the inside of this. But it's not one that we've done, and so doesn't really fit the techniques we've done. Now this one, if you let u be 2x, this would turn into the integral of the square root of u squared minus 1, and dx would be du over 2. And when you got square root of u squared minus 1, that's the secant substitution. So you would use u equals the secant of theta and work with that one. That trig substitution. This one, you could use a reduction formula, but since they're odd powers, you could let u be either sine x or cosine x because you got an odd in either one of them. And du would be cosine x dx. And so one of the cosines would cancel here. This would be u to the third. And the other cosine would be squared, and so that'd be 1 minus sine squared, and you use u for the sine squared. Multiply things out and integrate. Number 4 looks like a great candidate for integration by parts. Get this to drop down and integrate this part because we know that the derivative of tangent secant squared, so we'd set up the uv and let u be x and its derivative would be dx. dv would be secant squared x dx, and v would be tangent x. And we'd work with that. And you might have to integrate tangent, which is simply sine of x over cosine x. And so I do a substitution on this. Let's say let u be the cosine of x, and du would be a sign that would cancel the sign. Okay, so that's kind of the outline. I would do that one. This one looks like a trig substitution. It's a would be 3, so that's 3 squared minus x squared. And that's lined up to be x equal a sine theta. Do the trig substitution on that one. The next one's a little bit strange. We have not done a lot with cubes in the square root. So this one is essentially not a fit for some of the methods we've done so far. Likewise, sine to the 3/2, we haven't done much with that. Now there might be some things you could do with that one, but we haven't really talked much about sine to the 3/2 or square roots of sines or something like that. So that one's probably not a great fit. This one is not too bad. You could let u be x plus 1. Then this would be the u to the half. And this would be, x would be u minus 1 quantity squared. So u minus 1 squared, you could multiply out and take it times the u to the 1/2. And that would be pretty easy to integrate. This one, number 9, looks like it's a partial fraction one. So we'd set it up as the integral of a over x plus 1 plus b over x plus 2. And since this happens 3 times, we'd have to have a couple more here. C over x plus 2 squared plus d over x plus 2 cubed. Then figure out what the a, b, c's, and d's are. And then we can integrate each of the pieces, doing u substitutions for x plus 2 on each of these, and this one would be just ln x plus 2 times whatever b was, and this would be ln x plus 1 times whatever a is. And the last one, to the fourth, looks kind of scary, but really if you just let u equals x plus 12, then a du would be just dx, and so this would be just the integral of du over u to the fourth, or integral of u to the negative 4 du, which is pretty straightforward. So that's the first 10. Now I'm going to get you hints on each of the following ones. So like number 12, this one looks like it should be partial fractions. So I have x, so I'd put a over x. Then I have an x minus 1 squared, so I'd have to do an x minus 1 with a b, and a c over an x minus 1 squared. And then figure out the a, b's, and c's and do integration by partial fractions. This one looks like x squared plus 9, and so if a was 3, this would be a x equal 3 tangent theta trig substitution, x squared plus a squared. So I would use that substitution. On 18, I would start it off, because the degree is less than the denominator. I would do partial fractions on this one, because I have x, and x squared plus minus 1 is x plus 1 and x minus 1. So I would set this up as the integral of a over x plus b over x plus 1 plus c over x minus 1. And then I would figure out the a, b, and c's and integrate it. And it'd be ln x times whatever a is, plus ln of x plus 1 times whatever b is, and ln of x minus 1 times whatever c is, plus c. This one is not as simple to come up with. Now, what we might try to hear on this one is to let u equal x squared minus 1. Or we would use a trig substitution. This is like x squared minus a squared. I think I would use an x squared minus a squared. Yeah, I think I would. So, because if I just do what I was going to do there, then I'd get a 2x, and I would cancel one of the x's, and I'd have to figure out what x was. And solving for this would create a square root, and I don't like that. So I think I would use a u substitution for x squared minus 1, and that when it's x squared minus a squared, that's a secant substitution. A would be 1, so I'd use x equals 1 secant theta, and work my way through that with that trig substitution. This one is a slightly kind of tricky. We're not used to doing cubes, but that with the square root up here of x, that actually works out pretty well. In fact, if you let u equal the square root of x, then, no, I don't want to say that. I'll say it this way. I want this to be u squared. So I'm going to let u squared be x to the third. And so now I'm going to solve for x, so that I know what u is. So to get rid of the 3, I would take the cube root, or the 1/3 power, on both sides. And so I'd let u to the 2/3 be x. Now, that would change. See, this is x to the 1/2. So I would have u to the 2/3 to the 1/2 for the numerator. But I might not even want to do that. And then for the denominator, I would have x squared plus 1. But what would I use for dx? Well, if I take the derivative here, I would have u to the derivative would be 2/3 u to the minus 1/3 would be dx, du on here. So if I do that, I get a 2/3 u to the minus 1/3 du. And this would be, u squared would go in here. Because u squared was x to the 3rd, if I go back to what my original substitution. Now, this u to the 2/3, u to the 2/3 times 1/2 would be u to the 1/3, and this would be u to the minus 1/3, and so those are, this is underneath that one, and so they would just cancel, and I'd have the 2/3 I could take out. So this is the substitution I would use. Now, you may want to look at that a little differently, but that's basically the substitution I would use. Either thinking of it this way or thinking of it this way. If I start this again, I could say u squared equals x to the 3rd and take the square root of both sides to find out what u is, and that would make it u be this. That might be easier to look at for you guys. So yeah, use this one and it'll make sense when you try that. 27. This one had me stumped for a little while. I had to think about it for a second. Then I realized that if I multiplied the numerator by e to the t and the denominator by e to the t, I would get the integral of e to the t over e to the t times 3 and e to the t times e to the negative t. We'd add the powers and we'd get 0, and e to the 0 is 1. And I think then a simple u substitution for 3e to the t plus 1 will make this work out pretty easily. On 30, well, I have both of these to odd powers. Usually we like to leave even powers. So if I let u be tangent, its derivative would be secant squared, and that would turn this into odd power. But if I let u be secant of y, the derivative would be a secant tangent. The tangent would be gone, and this would be secant to the 4th, which I think I could deal with. So I'm suggesting that you try u equals secant of y. On 33, this looks like it's going to be nasty, but it really isn't too bad if you factor x to the 4th out of the inside. See, that would be 1 plus x to the 3rd dx. And this would be then the square root of x to the 4th would be an x squared. And inside we'd still have 1 plus x to the 3rd dx. And this would be pretty easy if you let u equal 1 plus x to the 3rd. 36. 36 is one that I would do long division because this is a higher degree than this. So I do x to the fifth divided by x to the third minus 1. And this would become, go in there, x squared. X squared times x to the third is x to the fifth. X squared times minus 1 is minus x squared. Draw the line and change the sign so we can add, and we get x squared. And so I would put that over what I was dividing by, plus x squared over x to the third minus 1. So this would be the integral. See, there's an x squared, x squared. That's pretty easy to do. Plus the integral of x squared over x to the third minus 1. Split this in two integrals. Do this one separately, the straightforward one. Do a u substitution for the denominator, and I think the derivative of this would cancel the x squared and be pretty straightforward. And then 39. This one, I think just letting u be x plus 1, then du would be dx, but also u minus 1 would be x, and so you could square it, put that in there, and this would be u to the minus 1/2 when you bring it up in the numerator and multiply it out and integrate it. On this one, the square root of x looks like wouldn't be very nice in there, so I probably let u equal the square root of x. Du would be, see, that's x to the 1/2, so it'd be minus 1/2, so it'd be 1/2 x to the minus 1/2 dx. So that would mean that that's 1 over 2 times the square root of x dx. So if I multiply both sides by 2 square root of x, I get 2 square root of x du equals dx. And so this would become the integral of square root of 1 plus u. That's what this would become. And then we'd have times 2 square root of x du, but the square root of x is just u. So this is the integral of square root of 1 plus u times 2 square root, or times u du. Now to make this work, I would probably let a second substitution, v equal 1 plus u, and this would work out. Now, it might have been easier to start this one. I haven't even thought about this. I'll think about it now. I might let u be 1 plus the square root of x. Then du would be exactly the same thing we had before. 1 over 2 square root of x dx. And then this problem would become the integral of, this was u, so u to the 1/2. That would be all of this. And then times 2 square root of x du. And the square root of x would be u minus 1. So then if you put that in for the x, square root of x, and multiply it out, I think you can integrate that. All right, 1 second to blow my nose. All right, number 45. 45 looks like we ought to be able to do this one by integration by parts. And the reason I say that is because we don't know how to integrate ln very well, but we can take the derivative of it. So I'd let u be ln of x squared plus 9, and v be the dx, and then the derivative of this, and you got to be real careful on this, derivative of ln would be 1 over the x squared plus 9 times the derivative of the inside, which is times 2x dx, and the integral of this would be x. So this problem would turn into uv x ln of x squared plus 9 minus the integral of v du, which would be times 2 and another x over x squared plus 9 dx. And then I think I would do, at this point, look at this and look at this and say this looks like a trig substitution, and I would let let's see, that's x squared plus a squared, where a is 3, so I'd use the tangent one, so I'd go x equals 3 tangent theta and try to do trig substitution on that part. 48. Real tempting to let u be all of this inside, but if I let u be e to the x, I think this might be a little bit easier to do than letting it be all of the inside. And maybe not. Now, I'll show you what I was thinking here, and then I'll show you and then we'll try the other way too. So if we let u be that, du would be e to the x dx, and so the e to the x would cancel this, and in here I would have then the integral of, I'll just write it, e to the x, this would be square root, this would be u squared minus 1 du over e to the x, and the square root of u squared minus 1, trig substitution for this, a secant one would make that one work. Let's try letting u equal all of the inside. E to the 2x minus 1. Then du would be 2e to the 2x dx. And so this original integral would become, I'd have the e to the x, and then I'd have the square root of u, and du would be over 2e to the 2x. Yeah. And so then if I solve this, I would subtract the powers because this is division. So I'd have the integral of, this is e to the x squared, so one of them would cancel, and I'd still have an e to the x in the denominator, so I'd have the square root of u over 2e to the x dx, subtracting the powers, x from 2x is x, and I think I could solve for e to the x in this, but I don't think it's going to look very nice. I would add 1, that'd be u plus 1 equals e to the 2x. And to solve for x, I'd take it to the 1/2 power. I'd get rid of that, so I'd have the square root of, basically, of u plus 1. So this denominator would be square root of u over 2 square root of u plus 1. And I don't think I like that one. I like this one better. And doing a trig substitution, u squared, x squared minus a squared is a secant substitution. So I let u equal the secant of theta. And do this one. Number 51. The power is higher than this, so I think I'd do long division. X to the 4th minus 1 into x to the 5th. That would go in x. X times this would be x to the 5th minus x. Draw the line, change the sign so I can add, and I would have an x. So I'd have plus x over what I was dividing by, x to the 4th minus 1. So this would turn into the integral of x, easy one to do, plus x over x to the 4th minus 1 dx. This is easy to integrate. This part I would probably do in parts, partial fractions. So I would let this be integral of x dx plus integral, and I would let the x be something here such that, or let this be this x to the 4th minus 1 factors to x squared plus 1 and x squared minus 1. This factors to x plus 1 and x minus 1. So I do a over x plus 1 plus b over x minus 1 plus this one doesn't factor, so, and it's a quadratic, so I'd have to do cx plus d over x squared plus 1. Figure out the a, b's, and c's and integrate that. Probably have to do a trig one on this and separate it. Messy. Fortunately, that's pretty easy, that first one. On 54, 54's got this ln with some x's, and I'm thinking integration by parts, letting ln be the u and x to the 3rd dx be the v dv. Derivative of this is 1 over x dx. Integral of this is x to the 4th over 4. So I'd have uv minus the integral of v, that's x to the 4th over 4 times this, which is 1 over x dx. This would cancel one of those x's and make it a 3rd. Pretty easy to do. We've already done that. So that one comes out pretty simply. And this one looks like a straightforward trig substitution, x squared minus a squared, where a is 6. And so I'd let theta x equal 6 secant theta. And do a trig substitution on that one. And that's how I would approach each of these problems.